Thanks a lot for the kind introduction, Heidi. It's a great pleasure to be here with all of you today, and I'm just going to talk a little bit about what we have been up to the last 4 to 5 years here at the department. Actually, before I start, I was going through the slides yesterday with my partner Caroline, is over there, and she told me, "Oh, you should go a little bit, make it a little bit more personal." I was like, "Okay, it's not a TEDx talk, but I will try." So how I ended up here? I was thinking about like, oh, shall I start with some like cringe general things like, it was always my plan to become a professor of natural language processing, work in natural language processing. Actually, I didn't know anything about natural language processing up until I became a master's student here at the department, and I had really the opportunity to study with Mark, and also Rob and Mark taught me the secrets of natural language processing. And so before that, I studied computer science, and I studied computer science because I wanted to become a game developer, but I realized that the fun part of game developing, it's on the artistic side, on the design, not on the software engineering, I guess. So I thought of probably I should do something else. I also wanted to become a professional basketball player, but I was never that talented. So all these things went out of the way, so I had to do something. So after my master's, I really enjoyed actually the process of researching new ideas, come up with new ideas and testing them. And I really believe that still the university is the right place to pursue research that might be interesting to you personally and make impact at the same time. So this kind of flexibility and freedom that we have at the university, we should not be taking it as granted. And this is something that I really enjoyed. And I'm grateful to Sheffield actually, because in a difficult or let's say weird time for my career, where actually I was applying for faculty positions, Sheffield, the information school, and later the computer science department, provide me this opportunity to come back to academia and do research for the sake of research, actually things that I'm going to present you here. Okay, so let's get down to business then. I'm going to start, this talk is going to have two parts. In the first part, I'm going to start with an introduction to natural language processing, current language technologies, and how we can actually develop these remarkable systems using neural language models, applications of language modeling, and then some challenges and showcasing a little bit of different types of work that we have done for tackling these challenges. So let's begin with an introduction. How many of you here have used ChatGPT? Okay, yeah, that's expected. Right, okay, so this is where we are now. Actually, you can write something to a computer program. Usually this is called a prompt, and it comes up with a remarkable answer like this. So the prompt here is, can you write a short analysis of the song Common People by Pop? And ChatGPT generates something that it makes sense. Actually, it's really good. So the song is indeed about cultural appropriation and romanticization of poverty by a rich person. And if you try to dig further of what this model can do, if you prompt it with a question such as, can you give me specific examples of cultural appropriation in the lyrics of the song, the system is ChatGPT is gonna come up with, again, a very good answer. She came from Greece, she had a thirst for knowledge, and actually I came from Greece, I had a thirst for knowledge for my master's, but because I was paying the tuition fee, I was like very, very thirsty. But actually you can see again impressive answers, right? So her desire to immerse herself in a different culture could be interpreted as a form of cultural tourism and so on. And then if you try to do some sort of like style transfer to make the model to generate text that might go a little bit beyond of what we know about the song. So can you write lyrics inspired by common people for 2010's Britain? Let's see if it is creative. Again, it comes up with an awesome, really amazing response. Avocado treats, yes, social media feed and so on. And then again, if you ask the model to convert the song to an opera, it's gonna do it. It's gonna convert that into an opera. And again, it's I really enjoyed the output from these prompts. Okay, so how we ended up there, right? And how even this is possible. Actually, by the way, I really like science fiction, and many works in science fiction have thought about highly sophisticated computers that can comprehend human language, reason, effectively communicate with humans, and in general, systems that have some agency. So many people now in 2024 think that ChatGPT is more like HAL 9000 in 2001 Space Odyssey. So if Dave asks open the pod the bay doors HAL, HAL has some sort of agency and might deny the saving Dave. But I don't think that actually we are in this kind of ballpark. I think we are somewhere closer to what the brain does in Isaac Asimov's collection of stories, I, Robot. And the brain, it's a computer, it's a positronic brain machine that can do supremely good in deduction, but it's an idiot savant. It doesn't really understand what it does, but it does it really well. I think this is where we are in terms of what ChatGPT can do. And I'm going to try to explain why I came up with this kind of theory, let's say. Okay, so before we talk a little bit more about if ChatGPT truly understands and comprehends language like humans, let's see how this language models works. What is language modeling and how we can do it with a family of neural networks called transformers. Actually, even the terminology of neural networks might be wrong. It shouldn't be called neural networks because it's a bunch of multiplications between vectors and matrices, or vectors and vectors, but actually using the word neural might make people think that these systems work like human brains, which I'm not quite sure. Anyways, what is language modeling? Language modeling is a very simple task. So actually in computer science we like to think in terms of functions. Function is something that you give an input and you take an output. You give something, you take something back. Now, in terms of language modeling, you give a sequence of words. Usually, this is called context or prompt. And the output, what you take back, is the most probable missing words. So here, for example, we have this sequence, acting monkeys are the best. As input, we want to build a system in that in the output is going to choose the most likely word from a set of predefined words that make our vocabulary. So in the output, actually, we expect to see band. Okay, so there are two main approaches for training neural networks to do language modeling. The first way of doing it is by predicting the next token from a you get a sequence of words, and the task is to correctly predict the next one. Usually, those models that train to predict the next word are called causal or generative. Don't ask me why people use this kind of terminology, but this is how you will find them in the literature. But usually when you see these words, it means that the model goes from left to right, predicting the next token. And by training these models like this, you can have systems that do this kind of magic things, such as GPT. And this technology underlies Llama 2, Llama 3, GPT-3 models, and so on. Okay. Of course, it's not only next token prediction, but it's mostly next token prediction. I'm not going to go into much more details here. Okay, so if I wanted to show you an overview of how the next token prediction works, again, you have this input, then you have a transformer network. When I say a network, think about it, that you do some sort of like vector matrix multiplications followed by some other stuff that I'm not going to go into details here. Okay. So the second approach to train language models with neural networks is called masked language modeling, and here the task, the objective is slightly different. Instead of predicting the next token, this model is trained to fill in the gaps. And this is called masked language modeling. Notable models include BERT and Roberta, and this used to be the state of the art between 2019 and 2022-3 roughly. Okay, so masked language modeling, now the setting is a little bit different. Randomly, we roll the die and we mask some of the tokens in the input sequence, and then our transformer tries to predict all the masked tokens. So here, Arctic monkeys, the best is the context. If we mask the first token, we try to predict A, and in the second case, band. Okay. All right. So how we do it, right? Let's see. Let's go now into a bit more of details about this. So we have an input sequence, and neural networks, as I said a little bit earlier, work on vectors and matrices. So we have to convert the text into vectors. Vectors are arrays of numbers. So to model a sequence, we have a sequence of words, and also we have information. We want to capture information about the positions. Okay, so each sequence is represented by the words themselves, and also by numbers, where each number denotes a particular position in that sequence. Okay, this is called and we represent those with vectors this way. So, for example, for the first word Arctic in the position 1, we have two vectors. One is the word vector itself that represents one particular word, and also we have one vector for the position. Okay, so we add those vectors together, and we obtain a new vector that represents some sort of like specific information about the word in that particular position, if I can explain that in 10 seconds. Okay, usually now you might have context size. This is like BERT-style models 5 years old. The context size, the maximum sequence length that we can model is around 512 tokens with vocabulary sizes of around 50,000. Now we can actually have models that are much larger with much larger vocabulary and context size probably in the thousands, or even lately Google announced that they can support sequence lengths that are even bigger. Okay, let's now go a little bit even deeper how the transformer works. Again, I'm going to try to explain the transformer in 1 minute, but bear with me. It's not very difficult, but actually what I want you to get is the rough idea of how this model works. So we have these vectors that represent position and word information for each token in the sequence. Okay, the transformer consists of two main components. One is called self-attention, and the other is a feed-forward component. So in the self-attention, what we try to do is we want to use information from all the tokens, from all the vectors that represent individual words in the sequence, by computing some sort of like similarity between them. So we compute similarities between vectors, and then we normalize it. So, for example, if we want to make a prediction for the word mask here, actually we compute the similarity across all the different vectors using, I'm not going to go again into details, using it's called dot product. And then we normalize it. So we get a weighted average of all these vectors, and the resulting vector is fed to the next component, which is a feed-forward layer, which is again a multiplication between the vector and the matrix. We repeat that k times for the self-attention, n times for the transformer. At the end, I don't want to, it's okay, it doesn't really matter if you don't really understand what's going on here. In the end, you're going to end up with a vector. Okay, so at the end of this process, you're going to end up with a vector which we usually call a contextualized representation of the particular token, right? And it contains information from the token, from the word itself, and all the surrounding context. Okay, but how we can do prediction? In order to make a prediction, we multiply this vector with a matrix where each row represents a particular word in the vocabulary, and by applying a function that normalizes this course into probabilities, we then choose the word with the highest probability across the vocabulary. And hopefully, this is going to give us the word R if we do that, if our model is accurate enough. Okay. So how we pre-train these models? Usually we use data that are publicly available from the web, Wikipedia, books, or even code, actually data from multiple languages. And we start with some sort of random initialization of these matrices that I try to explain to you that the transformer, the neural network includes. And through an optimization process, every time that the model makes a mistake, a wrong prediction, we adjust the weights and the parameters of the model accordingly. Okay, so this is pretty much how you can train a ChatGPT in probably 5 minutes. All right, so when we have trained our model, we can adapt it, or as we say now in machine learning and natural language processing, we can fine-tune it to a downstream task. So for example, if you wanted to do movie review sentiment analysis, you can actually make the model, specialize the model to perform particular tasks. So actually, we replace the output layer of the transformer. We take this out, and we replace the vocabulary with the particular classes that represent that we have in our data. So for example, if you do sentiment analysis, you might have data that are labeled as positive, neutral, and negative. Okay, and then we repeat the optimization on the training data of this particular task and adjust the weights accordingly. And hopefully, the resulting model should be able to accurately predict the correct sentiment of a given movie review. Okay, and then you can do that for various other tasks, topic classification and so on. Okay. Right, after we have trained our LLMs, we can use them. And during the last 4 or 5 years, we have done a lot of work on different application areas here in Sheffield. We have done a lot of work on computational pragmatics, analyzing speech acts, complaints, parody, and bragging, typically work led by Danai and Mali. Also, we have worked a lot on computational social science with applications in analyzing political ads, misinformation, influencers, and point of interest. Again, work done by Danai, Yida, and the rest of the team. And finally, we have done a lot of work on computational law, various tasks, legal judgment prediction, given a particular description of a legal case. Can we build models that can accurately predict the final outcome? And also document classification. Again, that's work that we have done with colleagues in Athens, Ilias and Theon. Okay. Large language models are very good tools. They work really well, but there are specific challenges in the development and the deployment of those systems. One of the biggest problems is that the training and use of LLMs requires expensive hardware and compute time, and the training these models and using them have a large carbon footprint. For example, training a state-of-the-art GPT-3 model actually we cannot do that here in Sheffield, would take years of compute time and would cost approximately £4 million or even more. Also, these models have very large memory requirements, and it's not easy for researchers or actually stakeholders that don't have access to resources to use the technology. So it creates inherent inequalities in terms of who is able to innovate and develop language technology. Okay, so what we have done so far, we have done a lot of work on on improving pre-training time for masked language models, and also work on memory efficient LLMs, how we can actually make the attention mechanism of the transformer more parameter efficient, and also how we can reduce the vocabulary size of the models. And this is work that was led mainly by Huyin, and also we worked on pre-training with Atsuki, George, and Katerina. Apart from computing resources and being carbon inefficient, LLMs require large amounts of data. Not only for pre-training, because okay, you can download the entire web and train your model, but actually you need labeled data. Labeled data that have been annotated by humans. But in, for example, industrial applications, this data is usually not labeled. So how we can effectively choose which data points should we label? And data annotation is expensive, and a very interesting fact is that humans are more data efficient than LLMs in the sense that we don't really require lots of different examples in order to learn how to perform a task, whereas LLMs might need thousands of examples. Probably not anymore, but actually they do. Okay, so what we have been doing here, we have done a lot of work on active learning, which is an area of like a machine learning paradigm. And the main goal is how we can choose informative data points in order to send them to humans for annotation. And we have worked on devising new acquisition functions, and also the application of active learning approaches on in-context learning, how we can reason with GPT-style models. And this was work that has been done by Katerina during her PhD. Also, with colleagues at Amazon, we have worked on weak or semi-supervised learning, and the idea here is how we can take unlabeled data and have machine learning systems that can provide accurate labels for them. So just taking the humans out of the loop here. Right. Apart from data and computing efficiency, another major issue with modern LLMs is the fact that it's hard for humans to comprehend what they do, and it's also very, very difficult to interpret the predictions. One major problem is like why an LLM made a particular prediction. We have worked with George on that, on a task called rationale extraction. It's a very simple setting in the sense that for rationale extraction, what we try to do is we try to identify which parts of the input are more important in order for the model to make a prediction. So if you remember this sequence of words that we saw earlier, for rationale extraction algorithms try to automatically identify which parts of the input are more important. Also, we have done a lot of work on faithfulness of rationales on faithfulness rationales analysis, and also new evaluation metrics. Again, work that was led by Cass and George. And finally, apart from all these technical problems, one major area of debate in the social sphere is what are the ethical implications of the development of LLM? Some people call we should stop doing research on language models entirely, or what about regulating technology? So, for example, the European Union said, oh, we should ban the technology whatsoever. In France, they banned the use of the development of AI algorithms in the legal domain. But actually, those systems might be useful for analyzing the law. So actually, with legal experts, we have done a lot of work on ethics and regulation, and we provide a little bit of an inclusive view of how we can see things in terms of what are the ethical limits on NLP development, and also how we should see regulation of large language models. Okay, so that's pretty much it for a high overview of what we have done so far in those different areas of natural language processing. And in the second part, I'm going to talk a little bit about the more fun. I mean, all of these projects were fun, but if I had to choose which one was like more fun, it was this line of work that I'm going to present you here, because it started by some random discussions that I had with my students probably 4 years ago, and I was like, okay, we should try do unconventional things that go against norms of natural language processing research, let's say. Okay, so it's more like I don't know if I can say this. In France in 19th century, some artists thought, okay, probably it's not a good idea to paint white rich people or saints of the Catholic Church anymore. We can do something else, something that we really enjoy, just for the sake of it. So this was pretty much it, but not going against the church or I don't know, the elite. It was more about like some conventions that people in NLP follow, and usually this has to do what these models do. It's about agency, like do these models learn like humans, or actually they should be learning like humans? They should follow linguistic theories. And I was like, probably I don't buy it. Let's try to do weird things and see what happens. So this line of research is about tackling anthropomorphization of LLMs, and it focuses on this first point here. Do LLMs acquire knowledge like humans? Still don't know, but I'm going to show you what we have found. Okay, so in the first line of research, we try to look if the pre-training, how you pre-train the model, affects what it learns about language. Okay, so the main premise of masked language modeling is that actually it's related, it's inspired by the closed procedure, which is a process from psycholinguistics to measure human readability and language understanding. And the idea is that, well, if you omit some words from a sequence and humans can correctly predict the words that are missing, this means that humans really know about the grammatical and syntactic information from the language, and they can understand the context. And that's actually, this is written I think in the BERT paper when they present their work. It's like, okay, right, what happens if we train LLMs following the closed procedure? Should be similar, right? Because the closed procedures show that humans that are able to predict missing words, actually they demonstrate linguistic knowledge. So that was the premise for using MLMs for training models. Okay, so, but how about if we use alternative pre-training tasks that actually might be more efficient as well and simpler? Can we train models to acquire linguistic models that way? So the first paper that we published in 2021 with Atsuki, George, and Katerina, actually we tried to see if we can just replace masked language modeling and train models. The idea here is that MLM has a very large number of classes. So when we make a prediction, the model should choose one out of 50,000, which is the size of the vocabulary. And if you have a larger model, that could be 100,000 or 250,000. And we thought, okay, that might take time. Let's make it simple. Let's try to devise binary classification tasks where actually you have to predict yes or no, 0 or 1, or choose one out of few number of classes, like 4 or 29 or 3. So what we have done is come up with 5 different pre-training objectives. One is called shuffle, where actually we shuffle some of the tokens in some of the words in the sequence, and the model, we ask the model to predict if the word has been shuffled or not. Then we randomly replace some of the tokens by other words in the vocabulary. The model is asked to predict if the word is original or has been replaced. And then it is a combination of both, shuffle plus random, and there the model predicts if the token is original, random, or shuffle. Then we come up with something that now groups together as a much larger number of words. We come up with 4 classes that might represent stop words, uninformative words, all of them are grouped together. Content words, and also we have some classes to represent special characters such as numbers and punctuation marks. And finally, we introduce even more abstractions, where actually the model is asked to predict only the first character of each individual word. So now each class contains all the words that start with a particular letter. So here, the class C contains car, cat, computer, name it. Okay, and this is the original one. This is what everyone was doing. So we train a BERT-based model, which is a standard architecture. I'm not going to go into details. It's like a transformer-based network. And as you can see, our objectives actually work close to the original MLM. Actually, here in natural language understanding benchmark, we are a little bit better. And for question answering, we are very close. Note that these tasks, compared to MLM, are much faster to train. Okay, so we wrote this paper, and then I could convince my next PhD student to start working on that. So Ahmed joined the group, and we said, okay, let's now look, let's try to do a little bit more abstract stuff, and also see how the pre-training objective affects the linguistic capabilities of the models. So how you do that in the NLP literature is something called probing. Probing for linguistic models. If you remember, as you pass these vectors through the transformer, you end up with a vector called the contextualized representation of the word. Okay, right. You take this vector, and on top, you train another model that tries to predict different linguistic features on text. Okay, and that could be grammatical information, sentence length, syntactic structure, and so on. The idea is that if this representation encodes linguistic knowledge, you're going to get higher performance on these simple probing tasks. Okay, I really hated probing at the time. I never said to Loic, who was one of the authors in Kono et al. 2018. But anyways, the idea here was like, if you do different things, what is going to happen? It should be, so if you do random things, you should get random results. Okay, well, let's see what we have done here. So, we grouped this kind of pre-training objectives in 2 different groups. One is called linguistically motivated objectives, or tasks that might make sense for humans. Okay, and also a group of tasks that if I ask you to perform it, probably you will never do it if I give you the text and the output. Okay, so we have here these tasks that we have used in the previous paper up to the first character, and we introduced 2 new ones which we call ASCII and random. This is a different random than the other random that I presented earlier. Okay, so for the ASCII pre-training task, I think we thought that this is impossible for humans if you don't really know the secret, is that, okay, let me start first. What is ASCII if you are not in computer science? ASCII is an encoding standard for electronic communication. It's pretty much mapping characters into numbers, okay, for computers. The idea here was like the task was to predict the sum of the ASCII code values of the characters in a particular masked word, modulo 5 for a 5-way classification. I might have said many probably weird words here. I'm going to try to explain what is it. So if you have the word cat, the ASCII value of C is 66, the ASCII value of A is 65, and T is 84. If you add all those together, you get 215. And then the modulo 5 is the remainder of the division between 215 by 5. That's give you 43. No remainder. Remainder is 0, and that's the value of the modulo operation. If you actually do modulo 5, you guarantee that you get remainders between 0 and 4. Why we did that? Because we wanted the 5-way classification task. Okay, we could have done something else, but we said let's do it like this. And also, we went a little bit, even a little bit extreme, by saying now every single time that we have a particular token, we are going to roll the die, and we're going to assign it to a particular class. So if you see, if we have the word cat, we might assign it to class 0 randomly. But every single time that we find the word cat in the pre-training data, it's going to belong to class 0. Okay, and we do that with all the words in the pre-training data. So of course you can see we might get completely unrelated words grouped together in the same class. I guess for humans this is an easy task if you know the mapping between words and numbers, but if you don't know the mapping, it's very difficult or probably impossible. And the model doesn't really know the mapping. I mean, okay, so some details about the probing task. We have 9 standard probing tasks. It's about predicting surface information, syntactic and semantic information. Its task consists of 100,000 sentences, 10,000 for validation and 10 for testing. And then we train a model on top of the BERT representation. People used to do logistic regression, a very simple linear model, or actually train another neural network on top of the representation. I don't remember, Ahmed, what we did in this case.
I think we did both.
We did both, there you go. Okay, so, right, we expected from the beginning that the tasks that are intuitive for humans, such as MLM, should be better. And we found that actually it doesn't really matter that much. With a random pre-training objective, you can be almost equally accurate to predicting the sentence length. And then if you do ASCII, actually you are better than MLM for predicting the syntactic tree depth of a sentence. And for predicting the tense, everything looks like close by, apart from random. But actually, random, it was a little bit hard to train. Okay. So however you train these models, you get good results. What happens, right? And one hypothesis that we have, why is this happening, is because these models do not really learn syntactic or semantic rules or grammatical rules from a textbook. They just learn statistic co-occurrences in the text, so patterns that from combinations of words that appear frequently in the text. Okay, so we have done that, and if you remember, we decided to group words that are unrelated at the output in the classification part of the network. Okay. So now, we decided to go a little bit the other way. So to group words together in the input. And I'm going to explain what I'm trying to say here. We want to go against the vocabulary orthodoxy of representing one word with one vector in LLMs. So typically, all these LLMs map by default each word to its corresponding vector. So there's one-to-one mapping, one word, one vector. And why we do this? Because the model should learn distinctive information for each token, and also there's this distributional hypothesis from Firth in the 1975 that words that appear in similar contexts should have similar vectors, and words that actually are irrelevant should be further apart. So play and plate should be similar, gold and silver should be similar, but silver and play should be further apart. Okay, so one problem with one word, one vector from an efficiency point of view is that the embedding matrix, the size of the embedding matrix, scales linearly with the size of the vocabulary. So every single time that you add new words in your vocabulary, you have to add one more vector. Okay, so we said, okay, how about if we group words together with some sort of criterion, and we assign them to one vector, okay? So that's going to reduce the number of parameters. Or actually, it can increase the number of tokens that we can model with our model, probably in as many as we like. Okay, so that was the main premise of working on this project led by Huyin called hash formers. And the main idea is to use hash functions. Again, it's a function, right? Hash function, you give something, you get out something else. In hash functions, you give some text or something, and then you get an index. You get a hash value, then you can use this hash value to squash it to a particular value, a particular index. Okay, so we use hash functions to map text of arbitrary size to fixed size values, and that way, this is the embedding matrix that I showed you earlier, the blue matrix. Now, every single time that we have a new word, we use this hash function and we obtain an integer value I, and this I corresponds to one vector in that embedding matrix. And then we use that on the transformer network, okay? So we don't really change anything to the architecture, we just change stuff in the input. So we have two ways of grouping tokens together, grouping words together. One, the first logical idea here was to group together words that might be morphologically similar. So, for example, play, place, and played should be mapped into the same vector with high probability. And this can be done with a locality-sensitive hashing approach that guarantees you this kind of behavior. But then we said, okay, why not? Let's go crazy and randomly assign tokens into indices, into vectors. So we use the random hashing approach, and in this approach, probably if you have play and place, they are morphologically really similar, but actually you're going to get different indices. So they're going to be represented in probably in a different vector. Okay, and we expect that this should not be working. Okay, this should not be working. Of course, again, we train a BERT-based architecture, it doesn't matter. We use the shuffle plus random objective from Matsuki's paper because it works well, and actually we can't really do text generation in that case. We hash and bucket together tokens with the same hash index, and these models, the beneficial thing about these models is that the vocabulary dependent, so you can actually model whatever you want because you hash it and you get an index. Okay, again, we expected that a locality-sensitive hashing function approach should be better than the random. It was not. And also, we found that, well, on average in natural language understanding tasks, we are very close, even a little bit better than using one-to-one mapping between vectors using the MLM training objective, which again goes against this kind of what you might be thinking about the behavior of these models beforehand. Don't ask me why this is happening. We don't know. What I'm trying to say is that on the other side, people might make claims that, you know, might not be so accurate. Okay, right, we have done this. Now let's go to the final part of the research that I'm going to show you today. Right, can you guess what is, can you understand this piece of text? Yeah, I mean, yes, no? 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 Yeah, impossible, right? I think it's difficult. Okay, so how about if I help you a little bit? Yeah? Yeah. Yeah, okay, so that's easy, and probably you guessed correctly, humans are able to understand text consisting of words with altered or missing letters. Can LLMs do the same? Probably they can. Okay, so that's again work done by Ahmed and Katerina, published in EMNLP a few months ago. And what we try to do here, again, we try to train models under extreme settings of information loss and see how that affects predictive performance and linguistic capabilities. All right, so we have a variety of different models here. It might look overwhelming. What I'm going to try to say here to understand is that we have 4 families of models. One, we just only use a single character from each individual word to train a model. In the second case, we use only 2. So first, middle, last, first, last, 2 first characters, 2 last characters, first, middle, last, 3 first, 3 last. And also, Emine had a great idea of using vowels and consonants, a colleague that we were discussing this paper, using only the vowels, using only the consonants. Okay. And also, when we predict, when we make prediction here, we do the same. We predict this kind of like tokens that have been, we have removed the characters. And also, we try to predict the entire word as well. It works. Okay, so results again. This is the full word. This is training a BERT model and a transformer model using the full token, and that gives you, of course, the highest performance of 70.2. But actually, using only 1 character, you are just only 3% lower in average on average on various natural language understanding tasks. And also, gradually introducing information, you get better results. Actually, you can see that using the last characters might not be as good. Using consonants is better than using vowels. Which again is surprising, right? When we did these experiments, we thought that again, using only 1 character shouldn't be working. But actually, LLMs do it. They are very effective. Okay. Also, we did our favorite probing experiments, just to show that probably we should not be doing probing at all, altogether. So actually, the representations of a single character can predict accurately semantic and syntactic phenomena in the whole sentence, in a whole sentence, which it doesn't really make sense. Actually, interestingly, for tense, predicting the correct tense of the main verb in a sentence, you can see that sometimes it makes sense because the 2 last characters work. The models that are trained only on last characters work better than the first characters, because in English ED actually denotes the tense. But actually, you can see the full model is very close to those models that we have extreme information loss. Okay, so this is pretty much it. This is what we have done. What I have talked about is LLMs can be very effective when pre-trained with simple approaches, even sometimes approaches that might not be intuitive to humans. They are surprisingly effective even when tokens that are semantically or morphologically different are represented with the same vector, if we just relax this kind of strong assumption of one word should be represented by one vector. And also, they are very effective when trained under extreme information settings. So actually, when you ask them to do something, pretty much they do it. Okay, so that's pretty much it. And when I got the promotion, friends and my students asked me, well, what's next? It's like some ideas about the future. When I get this question, I always think about one of my favorite books by Haruki Murakami. Probably we're gonna just continue shoveling not cultural snow but NLP snow in the next few years. So our plans are working on memory efficiency. We really like it, and also with Atsuki we started working on cross-lingual adaptation of LLMs, again with collaboration with Alimi, and also work on in-context learning, LLM reasoning. Probably we might start doing some weird things with probing models and see how robust these models are. So that's pretty much some like bold strokes of what's going to happen in the future. There's a lot of work to be done. NLP is far from solved. And to finish, acknowledgements. Well, it's a great pleasure to work with these great people. It's a photo from last year from the group. Some people have left, graduated. They do other great stuff. Special thanks to former PhD students, George, Ida, Mali, Danai, Arij, and Elias. Have many kind PhD students. I'm not going to mention you guys. Former research associates Samuel, Cass, and Marina, and amazing collaborators. Some of you are here in this lecture theater today. Really enjoy working with you guys. I have to say, I left the best for the last. I don't know if Twin is here, but special thanks to Twin for making it possible and easy for us to thrust Jade. Actually, if we didn't have access to Jade 2, probably only 10% of this work would be possible. And we're very grateful for Twin and the university for giving us access to the resources. And also, last but not least, funders. This research was partially funded, not at the beginning, probably later, by EPSRC, mostly through the CGT, ESRC, Leverhulme Trust, and Amazon. That's all. Thank you.
Plenty of time for discussions or questions, I guess, before we go out. And I'm told there's tricks and other things out there. We mustn't ask how it works. We've been told about anything else. James?
Thanks, Nikos. Really lovely. I can see, so humans are trained on language with full information, and then they can solve the problem of partial information. You did it the other way around, you trained with partial information. I can see maybe it's hard for LLMs to be trained with the full information, then test on the partial because the tokens all get messed up and don't get recognised. Is there a way of doing the test for what the humans actually do and seeing if that works?
Yeah, we were thinking about it actually, and some of the reviewers asked similar things, and we didn't have resources to make the comparison. Actually, well, in the original experiments, Ahmed, what he did is that given this partial information, we're trying to predict the full information, the full token, and that still works. We haven't done any experiments with humans, but we would love that to see how it plays. Yeah, it could be on the character level, actually, just to answer your question. But Atsuki is working on cross-lingual vocabulary adaptation. The problem with state-of-the-art models is that heavily rely on English data for training, and that's understandable. But when you try to use them in different languages, for example, I don't know, in Greek or Arabic or any other language, it is much more expensive because of some of the tokenization problems. So I didn't really speak about tokenizers. Tokenizers are algorithms to how you decide to chunk the text into units. And all those methods are English, heavily biased towards English. So when you actually try to segment text in Greek, if you use ChatGPT, it's much more expensive using it than using it in English for the same length of context. So Atsuki, he's over there. Hopefully, he's doing some remarkable work in that front. So hopefully, we're going to have some results soon.
Great, thank you.
On efficiency and also how you can maintain accuracy as well, because again, those models are much better in English than using them in other languages.
So based on current work, if you train not English, or let's say if you don't have the component at all, then the accuracy of other language would definitely decrease.
Yes, that's correct. Yeah.
Yeah, Prof.
Nikos, thanks. A really interesting talk. When you were training some of these sort of weirder models, like the random and shuffling models, the ASCII models, and so on, you didn't say anything about the size of the training sets. Did you look at how that affects the results? I mean, how much data were you using? I guess also the complexity of the model. So you didn't really talk about that in terms of the parameters and so on and so forth. Did you investigate how these changeable things have an impact on the results?
Yeah, we haven't really. That's really interesting. We haven't really checked how the pre-training size per se affects the performance, and actually that might be something that we should be looking at. But what we did is we did an analysis of how much information you lose, because if we just keep 3 characters, probably you model some words fully, right, in English. All the stop words actually might remain intact. So in the paper we have an analysis on that, but yeah, we haven't really tried to see, if you use just a smaller number of data points, if you're going to get similar performance. Probably we should do it.
Yeah, it wasn't meant to be criticism. I just keep thinking about how LLMs are different from what humans do. And one of the standard things that's troubling is humans get nowhere near the amount of data that LLMs do to train on. So I just wonder when you have these sort of weirder models, if you start pushing down the amount of data that they have, they suddenly break at some point. And and stop performing as well as the ones that have the.
Oh, it's very likely, yeah. We didn't try, but definitely it's a good idea. Which I think with Ahmed now we look a little bit on distort the data during pre-training randomly. So actually just take some input sequences, introduce noise, and see what happens. But we don't have results yet.
So I'd be interested. So I've been doing some work on OCR, post-OCR text correction, the noisy scans of 19th century newspapers, trying to use language models for that, which is degraded text. So maybe we should talk sometime. I could learn something from you. But we're using standard language models, but they're able to do things with slightly degraded text, but then it really drops off at some point. But some of the techniques you're developing might help.
Might be helpful, yeah.
Thank you. Oh, sorry.
Yeah, mainly it's yeah.
Okay, thanks for the talk. I love the mirror coming through. You said a couple of times throughout the talk, like, we don't know the answer to this question, right? So do you have any ideas on how you would approach trying to find the answer out? Like, do you have ways to explore this space?
We don't. We don't. The difficult part of doing this kind of comparison between a piece of software and a human is that gathering human data, it's very expensive, and it should be only part of a large grant that we haven't gotten from this kind of research. So yeah, it's really difficult to see, if you just let's say do sentiment analysis, for example, by just giving them 1 or 2 characters, see how they perform, and that would be really nice. The reviewers told us, but yeah, we couldn't really provide the evidence.
So it's very much a lack of resources, like to be able to explore this.
It is lack of resources, yeah. I think it's, yeah, because you need to gather humans and ask them to do things and then compare with the model.
Cheers.
I think, yeah.
Yeah, so thank you very much, Nikos. I mean, you know, I'm not from a computer science background, but I find that incredibly accessible and interesting. So actually my question got asked earlier, which is great because I got to ask my other question. So I was wondering, in terms of, so we are, I think it's fair to say that our vocabulary is evolving, especially because of the internet and all the subcultures. So I wonder if we have any sense in terms of how well, when a model is trained on slightly older or more generic data, how well they perform on more newer, up-to-date, and sort of subculture.
Usually it's not good. Yeah, usually it doesn't work well. Actually, Ida was behind you. Has done work on this. Yeah, so we found, we had a paper with Helena as well. We found that actually, yeah, it was like on specific tasks on rumor classification. They don't work really well. And there are efforts on how you can update the models and keep them up to date with recent information. But yeah, if you just use one of these like models that I mentioned earlier, actually, I don't know. The Prime Minister of the UK changed I don't know how many times the last few years, right? So they might capture that Rishi is the Chancellor, not the Prime Minister. So we need mechanisms to update those models. And yeah, when you are out of the period that these models have been trained, usually they don't work well.
Thanks so much. So I'm not from computer science background as well, but I'm really interested in your talk. So I want to ask you questions about the last paper you presented about the linguistic capacity, linguistic performance of the LLMs. It seems to me that for the first kind of experiment, so which you only present the first letter of the sentence. It seems to me there's no information in that sentence. So, but as a result, the models can demonstrate a similar capacity of performance compared to you show the like 4 tokens. I was wondering, maybe isn't that show that maybe the model doesn't understand language, especially in the sense of whether they understand the semantic structure of human language.
We didn't want to be that open in our paper because it would have been rejected, but we tried to be a bit more diplomatic. I don't know. I cannot tell you. It might. I don't know. The human brains might be matrix vector matrix multiplications. Who knows? I don't know. Probably not. But in that case, what it demonstrates, though, I don't know if these models understand language like humans or have the same capabilities. What it means is that even if you tell them to do something that humans might not be able to do it, they're going to do it. They might do it, actually. Much better than humans, probably.
Can I have a quick one? Sorry, I think my point is, I think the first sentence, it's not even a language or a sentence. It seems to me the model just create a language or which has semantic.
I don't know, but probably it probably can pick up patterns of sequences of single characters that appear together. And let's say you want to predict correctly sentiment of movie reviews, then probably they identify some regular patterns in the data. Probably, as humans, we might be able to do that, right? But it requires a lot of effort. I don't know, but they can do it. So.
I saw your work. I saw your work that which plays method around with the tokens. Say you are designing that some embeddings that doesn't make sense at all. So I wonder that have you looked into the attention mechanism in such models? So which means that if you are, say, if you have a natural language text, so some part of it, some portion of it should be more similar to the others. So that's basically how humans are understanding the text. Say if you mention a dog is playing in the park and you mention it, and it refers to the dog. And so for the if you are treating the tokens normally, so for attention mechanism, the it will have a very high similarity with the token dog. And when you are aligning say different or representations that make no sense, will the attention map keep the same?
That's a very, very good point. We haven't really done any analysis on the attention mechanism. Probably we should have done it at the time. I don't really have any information like what's going on, but we didn't really look at it. We should have done it.
Yeah, I mean, if it's
very
completely different, then it means that it might mean that the neural network is learning some completely different linguistic pattern from humans. So if the attention map are say very similar to the original one, I think it might be that say the word embedding actually, even if the word embedding is say combined with multiple irrelevant words, the word embedding might say contains all the embedding information. So that means that it doesn't need that a large embedding to keep all those representations with different words.
Yeah, I think that's a fair thing to say. Probably this is what I want to say of what the transformer do. What the transformers do is that actually the representation that the contextualized representation that they learn for individual tokens are very close by. If you do cosine similarity between those vectors, it's like 0.95, the lowest one. They are very close by in the space. So actually, my premise is that it doesn't really matter how you represent the tokens or what is the order in the sequence. If the information is there, actually the model picks it up and makes correct predictions. Actually, having said that, there was a paper published in 2021 in the same conference where we did the different objectives, this random thing, from Meta, that actually went the other way around. So they just shuffled words in the input and they trained models, and they found that actually word order doesn't really matter. If you have all the information there, it still works.
Thank you.
Yeah, I have a question about the network architecture, because we know that the first transformer is the encoder-decoder one, but now recently it's become we only take the decoder-only architecture. Is there a certain reason that why it's better? And I think that the common method now for the training strategy, the predicting network is the common one instead of like the bird one predicting the mark. So I just wonder, is there a certain reason that someone is better, or yeah?
That's an excellent question. Actually, I think my personal opinion is that the architecture between BERT and the decoder-only GPT style models pretty much it doesn't have a lot of changes. Only the attention mechanism, right? So where you look, size and data, right? I think this is the key. The information, the architecture is pretty much the same, and also the secret sauce on top of doing supervised fine-tuning on specific tasks with human annotated data, and the reinforcement learning bit that makes the model to work much better.
Yes, thank you for your inspiring talk. In one of your last slides, you mentioned in-context learning as a future work group. So as far as we know that in-context learning has been already used in current, let's say, prevalent foundation model like GPT-3 and GPT-4. So can you give a little bit more concrete outline from which direction or from which aspects you are going to change in context learning in your future, or you are going to improve in context learning?
Yeah, so Means, he's over there, started doing his PhD now, and we look a little bit into context learning with C. I don't know, the first ideas that we try to explore is like data selection for in context learning, how you choose your few short examples in order to increase performance. Actually, we have done some preliminary work with one of my previous students on that. This is actually the direction that we are looking into it right now. And probably how you do in context learning in extreme cases when you have a very large number of labels, because currently people prompt LLMs, right? But they do it for binary or few way classification tasks. But what happens if you have, I don't know, 1,000 classes, right? Because you can't really pass everything into the prompt. I mean, in Gemini or GPT-4 probably you can pass a lot of things in the prompt. But let's say you use conventional academic models, what happens? So this is now the space that we are looking into.
I'm not sure if this question is well formed in my head yet, but it's now
ChatGPT too.
So, thinking about your experiments where you are taking language and you're doing something weird with it, like predict the model or whatever, or the ASCII code, whatever. It's still the case that underneath it all is natural language. And it's a bit like we're looking at language through a darkened glass in various forms of distortion and information loss and whatever. But you've still got huge amounts of language data there. I don't know if has anyone really looked at training large language models on synthetic data, completely synthetic data. There's nothing to do with real language, but it involves huge amounts of sequences. They discover correlations, and then you apply it to linguistic tasks.
Yes, actually, there is. We can't really give away all the ideas, but that's spot on. It's spot on. Actually, we have discussed that with Ahmed, and I don't know. We probably will do that something in this space soon. But there is work on summarization, where actually they use linguistic rules, syntactic rules, to synthetically generate data, not even from a language model. So basically they have nouns, verbs, all the part of speech, and they just fill in the gaps. They train models, and then they use them for summarization?
Yes.
Yeah. So they do that for summarization, and actually it works. It works better than training from scratch a summarizer.
Right. Well, the synthetically generated, so what underpinning this process of generating the synthetic data is stuff that's like natural language.
Yes, it looks like natural language, yes.
So it comes out looking and having characters. So I was thinking if you could try and find a basis for generating complex sequences which have correlations within them to be discovered by a large language model, but it's not rooted in natural language.
Okay, so
some sort of like probabilistic gene sequences, I guess, then you get used for that.
Okay.
But you could have, say, probabilistic networks generating symbol sequences, but they're not in any way related to natural language rules. So.
Okay, yeah, I don't know anyone that has to try this kind of things. Probably it's really interesting. We were thinking of going completely random with Ahmed and generate data.
But it may be that you can have data that has correlations to be discovered, but they're just not like natural language, and that will somehow, that's kind of what your system.
So you have some patterns in the.
Yeah,
so
there are patterns to be discovered,
and
that's how the network builds the strength within it.
we should talk about it. I think that's very interesting.